Welcome, everyone. Thank you so much for joining us for today's deep dive. We're unpacking a genuinely fascinating set of materials today.
We really are. It's a heavy one, but a good one.
Yeah, it explores South Africa's climate reality. We're looking at the human impact driving it, and ultimately what this actually means for our collective future.
Right. Yeah.
Because we want to cut through the noise, skip the standard dinner party debates and just look at the hard data.
Exactly. Getting past the rhetoric.
So the mission today is to answer this massive, heavy question. If the climate is always changing and if nature ultimately always prevails, how much does objective science actually say that we are speeding things up?
It is arguably the defining question of our time.
Yeah.
And I think grounding this entirely in the South African context makes it much more tangible.
Yeah, it is closer to home.
It does. We are taking the macro level atmospheric physics
Right.
and looking at exactly how they play out right in our own backyards, in our agriculture, our economy.
Okay, let's unpack this. I want to start with a phrase that you see printed on, well, every other reusable tote bag out there: save the planet.
Ah, yes, the classic slogan.
Right. And the material we are diving into today offers a pretty sharp reality check on that specific framing. Because geologically speaking, the Earth has been a snowball. It's been a molten rock. It has survived ice ages and asteroid strikes.
The planet itself is fundamentally fine.
Exactly. It isn't going anywhere. What is actually on the line here is our specific modern lifestyle. I love how it's brilliantly framed in the source material. What's at risk is our ability to grow mealies in the Free State.
That distinction is so crucial because it completely shifts the psychological framework of the conversation.
How so?
Well, we aren't engaged in this epic battle where nature either wins or loses. Nature is relentlessly adaptable over long timelines. The issue is purely about habitability for our species and the ecosystems we rely on.
Which is very different from saving a rock floating in space.
Precisely. And in the South African context, if you look at our unique biodiversity, specifically the Fynbos biome down in the Western Cape,
Oh yeah, Fynbos is famously tough.
very resilient.
Yeah.
It's literally fire adapted. It actually requires a specific burn regime just to germinate its seeds.
But that resilience only goes so far, right?
Right. It operates within a specific set of parameters. If you permanently alter the winter rainfall patterns that follow those fires, even the toughest, most drought-resistant protea eventually hits a physiological breaking point.
And the biome collapses.
Exactly.
Because you can only push a highly specialized, localized system so far before the underlying mechanics just snap.
Yes.
And understanding those mechanics is vital when we run into, probably the most common counter-argument out there. If you're listening to this, you have undoubtedly heard someone at a braai say, well, the climate has always changed.
And you know what? They're absolutely right.
They are.
The climate has always changed. The scientific baseline for these massive natural historical shifts comes down to what are known as Milankovitch cycles.
Milankovitch cycles.
Yes. These are the natural variations in the Earth's position relative to the sun. You have the shape of the Earth's orbit, which stretches from circular to elliptical. You have the shift in the Earth's axial tilt, and you have the wobble of the Earth on its axis.
Sort of like a spinning top losing momentum.
Exactly like that.
Huh.
And together, these orbital mechanics dictate how much solar radiation hits different parts of the planet. That is what drives us in and out of ice ages.
But the critical factor here isn't whether those natural shifts exist, it's the timeline. Because if I recall the orbital mechanics correctly, those cycles are incredibly gradual.
Very gradual.
We are talking about changes that unfold over tens of thousands or even hundreds of thousands of years. The ecosystem has time to slowly migrate and adapt to that. But what we are measuring right now is playing out in decades.
Precisely. The core issue is velocity. Natural climate forcings move at a geological snail's pace. The analogy used to describe this difference is stark. Natural climate change is like watching a slow, gradual sunset over the course of several hours. What we are experiencing right now is the equivalent of someone walking into a room and suddenly flicking off the lights.
Wow.
The velocity of the atmospheric change completely outpaces the biological capacity of most species to adapt.
Which brings up another great analogy from the text we should touch on, because it perfectly dismantles that whole "it happens naturally" defense.
The forest fire analogy.
Yes. Think of a forest fire. Lightning strikes, dry brush ignites, and a forest burns. That is a completely natural cycle.
Happens all the time.
Right. But just because a forest fire can happen naturally, that fact doesn't magically acquit a guy standing in the middle of the woods holding a jerry can and a lighter.
It really highlights a major flaw in logical reasoning. Pointing to the Milankovitch cycles of the Pleistocene epoch does not explain the thermal dynamics we are measuring in the troposphere right now.
So what does this all mean? If we are throwing out the natural cycles argument, how do we definitively prove the human element? For an audience that wants the hard evidence, how do we identify the specific accelerant we are adding to the system?
What's fascinating here is how elegant the objective science actually is when you drill down into it. We are talking about the smoking gun of climate science, the carbon isotope fingerprint.
The carbon isotope fingerprint. So this is effectively the CSI level of climatology.
That's a great way to put it. Yes, because carbon doesn't just exist as one uniform type of atom. It comes in different isotopes, primarily carbon-12, carbon-13, and carbon-14.
And the key difference there is the atomic weight and stability, right? Because carbon-14 is the radioactive isotope, the one archaeologists use for dating artifacts because it steadily decays over time.
Exactly. Carbon-14 has a half-life of roughly 5,700 years. Now, plants naturally prefer to absorb the lighter carbon-12 during photosynthesis.
Okay.
When those plants die, get buried, and are subjected to millions of years of heat and pressure, they turn into fossil fuels. Your coal, oil, natural gas.
Right.
And because they have been buried for millions of years, well past that 5,700-year half-life, all of the carbon-14 in those fossil fuels has completely decayed away. They contain zero carbon-14.
Oh, I see. So the fossil fuels are essentially a massive ancient vault of purely carbon-12 and carbon-13.
Exactly.
Which means when we dig up that coal and burn it, we are flooding the atmosphere with a highly specific, measurable type of carbon.
That is the exact mechanism. When atmospheric scientists measure the air today, they don't just see a general increase in carbon dioxide. They see a massive spike in carbon dioxide that is entirely devoid of carbon-14.
You can't fake that.
You cannot fake that chemical signature. It is not coming from volcanic eruptions, and it is not coming from recent deforestation. We are literally finding the biological signature of ancient burned plants accumulating in our atmosphere.
That is incredible.
The isotopic makeup of the air is changing, and the consensus is objectively clear. We are the primary drivers.
That is incredibly definitive. You aren't just guessing based on temperature graphs. You are tracking the chemical origin of the carbon itself.
The literal fingerprint.
And once that specific carbon is in the air, we know it alters the atmospheric density. We are changing the physical composition of the troposphere, effectively thickening the blanket around the Earth, which means it traps more thermal energy.
Yes.
And that thermal energy has to go somewhere.
It gets absorbed into the climate system, primarily into the oceans, actually, which profoundly disrupts the global water cycle. This is where the abstract chemistry becomes a very harsh, localized reality for us.
Because we see it in the weather.
You can see the symptoms of this trapped heat in recent catastrophic events. Take the floods in KwaZulu-Natal.
Devastating.
According to the Clausius-Clapeyron relation in physics, warmer air holds exponentially more moisture. So when that hypercharged atmospheric moisture hits a weather system, it doesn't just rain. It dumps historic volumes of water in a matter of hours.
Overwhelming infrastructure that was just never engineered for that kind of load. And on the flip side of that same coin, you have the severe multi-year droughts in the Western Cape. You have that trapped thermal energy expanding the high-pressure systems in the subtropics. It physically blocks the cold fronts that usually bring the winter rains to the dams.
It is the same underlying mechanism. More trapped energy. It just manifests at opposite extremes depending on the local geography.
Which perfectly illustrates the vulnerability. Here's where it gets really interesting, though. South Africa finds itself in a highly paradoxical position right now.
Very much so.
We are dealing with these massive climate vulnerabilities, the droughts threatening the Finbows and the agriculture, the floods wiping out infrastructure in KZN. But at the exact same time, South Africa is one of the most carbon-intensive economies on the planet.
We are deeply tied to coal.
Our entire developmental backbone is historically reliant on burning the very fossil fuels that are driving this isotopic shift.
If we connect this to the bigger picture, you are looking at the core friction of what is called the just transition.
The just transition.
Yes. Transitioning away from coal is not just an engineering problem. It is a profound socioeconomic challenge. You look at entire municipalities, particularly in Mpumalanga, where the local economy is entirely tethered to the coal industry.
It's the lifeblood of those towns.
It's the miners, yes, but it is also the transport logistics, the local retail, the municipal tax base.
You can't just mandate a sudden shutdown of the coal fleet. Not only do you have the immediate reality of a fragile power grid that needs baseload generation just to keep the lights on, but you would completely decimate those local economies.
The fallout would be immediate and devastating.
But conversely, keeping those plants running indefinitely locks in the long-term ecological and economic devastation of the extreme weather events we just discussed.
So the just transition is about navigating that incredibly narrow tightrope. How do you deploy renewable infrastructure and decommission the coal fleet at a pace that stabilizes the grid, while simultaneously retraining a massive workforce?
While creating new economic hubs in those specific coal-dependent regions.
Exactly. You are essentially trying to rebuild the engine of an airplane while it is in mid-flight.
It requires a level of systemic planning that goes way beyond standard environmental policy. And speaking of understanding these deep systemic changes, there is a fascinating layer to how we gather this data.
The historical observations.
Right, because long before atmospheric scientists were measuring the lack of carbon-14 in the troposphere, the actual shifts in the climate were already being meticulously tracked by local communities. The role of indigenous knowledge and local generational farming here is just incredible.
It is a phenomenal source of empirical data. You have local farmers and community elders who have lived intimately with the land for generations.
They know the baseline better than anyone.
They operate on observational data, what scientists call phenology, which is the timing of biological events in relation to changes in season and climate.
They weren't using satellites, but they were tracking the exact microshifts. They noticed when the frost dates began to arrive later in the year. They tracked the shifting migratory patterns of local bird species, the changes in the behavior of the wildlife, and the erratic timing of the seasonal rains.
They recognized that the underlying rhythms of the ecosystem were fundamentally altering long before it was ever codified into academic models.
It's amazing. Modern climatology and ecological science are, in many ways, finally catching up to and validating the localized generational tracking that these elders have relied on for survival.
It proves that you don't need a mass spectrometer to see the impacts. You just need to pay close attention to the baseline of your own environment.
Which brings up a major psychological hurdle for anyone paying attention. If you are listening to this and you understand the carbon-14 data, you see the extreme weather, and you grasp the immense difficulty of the just transition.
It is incredibly easy to just fall into pure fatalism.
Exactly. If the carbon is already in the air and the climate momentum is already locked in, why bother doing anything at all? Why not just accept the inevitable?
This raises an important question about agency and how we define our goals moving forward. Fatalism is usually the result of a binary mindset. We either fix it completely or we are doomed.
Right.
But climate science operates on a spectrum, which is why we have to clearly separate mitigation from adaptation. The analogy of navigating a massive ship is incredibly useful here.
Because of the momentum.
Exactly. Because of the thermal inertia of the oceans, the climate system has massive momentum. Even if we stopped all emissions tomorrow, the ship is still moving forward. We might not be able to stop the ship from hitting the iceberg entirely.
But the brakes still work. Even if you can't stop on a dime, bleeding off speed changes the physics of the impact.
That is mitigation. It is slowing the rate of warming. It is slamming on the brakes so that when we do hit the iceberg, it is a glancing blow rather than a catastrophic hull-breaching collision.
Every fraction of a degree matters.
Every fraction of a degree of warming that we prevent translates to thousands of lives and billions of rands in infrastructure saved. That is mitigation.
And adaptation.
Adaptation is reinforcing the hull of the ship for the impact we know is coming.
And what is genuinely inspiring is that South Africa is actively punching back on both fronts. We aren't just sitting around waiting for the collision.
Not at all.
If you look at the mitigation side, you see the massive rise in solar startups and decentralized energy grids. People are innovating out of sheer necessity, taking the pressure off the central coal grid and lowering emissions simultaneously.
And on the adaptation side, you look at the agricultural sector. The farmers growing those mealies in the Free State are deploying highly advanced water-wise farming techniques.
Yeah, they're really adapting fast.
They are utilizing precision agriculture, changing crop varieties to drought-resistant strains, and fundamentally altering how they manage soil moisture. They are adapting to the altered water cycle to ensure food security.
It is that inherent resilience turning into actionable engineering. So to synthesize all of this, the through line today seems to be that understanding the objective science strips away the paralysis.
It really does.
When you understand the isotope fingerprint, you stop wasting time debating whether the jerrycan exists, and you start focusing on putting out the fire.
Because knowledge is only valuable when it is applied. When we clearly see the mechanics of the Milankovitch cycles versus our current velocity, and we understand the socioeconomic realities of the just transition, we can direct our energy toward actual grounded solutions.
Right.
It focuses the mind on protecting the grid, safeguarding the workers, and reinforcing our agriculture.
And for you listening, this brings the macro data right back to your front door. This isn't just broad talk about abstract global concepts or theoretical modeling.
No.
We are talking about the long-term stability of the food in your local grocery store, the reliability of your power, and the resilience of your specific neighborhood against the next shifting weather pattern.
It's all connected.
The objective science shows we have accelerated the change, but it also shows we have the exact data needed to engineer our survival.
It demands a much higher level of environmental awareness from all of us.
It absolutely does. And we want to leave you with a final thought to mull over today. We discussed how local farmers and indigenous elders were able to detect the microshifts in the climate long before the scientific consensus caught up, simply by paying deep generational attention to the land around them.
Observation is the powerful tool.
So look around your own life. What subtle changes in your own local environment are you noticing? The behavior of the birds in your backyard? The shifts in your local neighborhood's weather patterns? The timing of the blooms on your street? What are you noticing right now that might just be the early warning signs of tomorrow's climate reality? Pay attention to the baseline. Thank you for joining us on this deep dive.